Hello everyone, this video is the sixth in my series explaining AIME problems. In this video, I'll be talking about problems with probability and the ways that they can be solved. I encourage you to pause throughout the video and try to solve the problems. Here are some general tips for probability problems, and many of these are from counting. You should always find ways to make the problem easier than it looks. You should find ways to make the problem similar to problems that you know. Finding the opposite of what you want can sometimes help. And it is always possible to change a method of doing a problem if you're stuck. Also, some new ones are sometimes finding a recursion can help to solve the problem, especially if finding smaller cases is easier. And many probability problems include algebra, geometry, and other concepts. Let's start with the problem that involves geometrical probability. A point P is chosen at random in the interior of a unit square, S. Let dP denote the distance from P to the closest side of S. The probability that 1/5 is less than or equal to dP is less than or equal to 1/3 is equal to m by n, where m and n are relatively prime positive integers. Find m plus n. Let's start this problem by drawing a diagram. This is going to be the unit square, which is 1 by 1. Then let's draw an approximation of 1/5 is less than or equal to 1/3 for each side. Now, after we've drawn it all, let's try to find which of these regions are not successful, which don't work. For certain, the middle region does not work, and neither do these regions at the ends. But what about the remaining regions? Do all of them work? No, there's still a lot to be cancelled out, since in these regions, it is too close to this side, and similarly in the other regions. Finally, our successful region is pretty small, and right here. Now that we have our region, what are we actually trying to calculate? Well, for geometrical probability, the probability of the event happening is the area of the successful region over the total area. So, in this case, this evaluates to 56 over 225, which now, after adding m and n, we get that the final answer is 225 plus 56, or 281. Here's a probability problem that involves casework. Jackie and Phil have 2 fair coins and a third coin that comes up heads with probability 4/7. Jackie flips the 3 coins, and then Phil flips the 3 coins. Let m by n be the probability that Jackie gets the same number of heads as Phil, where m and n are relatively prime positive integers. Find m plus n. Let's break this problem into 4 cases, where there's 0 heads, 1 heads, 1 head, 2 heads, and 3 heads. Also, let's assign for any configuration the third coin is the biased coin, since it said we have 2 fair coins and a third coin. So, for 0 heads, there is only one way that is possible, and this is going to be TTT. And the probability of this is half times 3/7. And we need to square it since both of them have to get the same value. For 1 head, there are 3 possibilities: HTT, THT, or TTH. And the probability of this is half times 3/7 times 2, since this happens twice, plus half times 4/7 squared. And for 2 heads, there are again 3 possibilities: HHT, HTH, or THH. The probability of this happening is half times 3/7 plus half times 4/7 times 2 squared. And for 3H, there's only one possibility, which is HHH, and the probability of this happening is half times 4/7 squared. And if we add up all of these values, our final probability is 246 over 784, which is the same as 123 over 392. So our sum of m and n is 515, which is our answer. Now let's do a probability problem that involves conditional probability. Charles has two six-sided dice. One of the die is fair and the other die is biased so that it comes up 6 with probability 2/3, and each of the other 5 sides has probability 1/15. Charles chooses one of the two dice at random and rolls it 3 times. Given that the first two rolls are both 6s, the probability that the third roll will also be a 6 is p over q, where p and q are relatively prime positive integers. Find p plus q. Before we can solve this problem, we need to know what conditional probability is. Conditional probability just means that the probability of A given B equals the probability of A and B over the probability of B. In this case, there are two cases, one with the fair die and one with the biased die. The probability of the fair die for P, A, and B is half times 1/6 times 1/6 times 1/6. The half factor is there because there's a 50% chance that he chooses the fair die. And we have to add half times 2/3 times 2/3 times 2/3 over the probability of B, which is just half times 1/6 times 1/6 plus half times 2/3 times 2/3. This evaluates to, after canceling off all the halves, 1 over 216 plus 8 over 27 over 1 over 36 plus 4 over 9, which evaluates to 65 over 102. And if we add m and n, or p and q, we get that the final answer is 167. Here's a problem that, although short, uses a concept that we have not talked about yet. 9 delegates, 3 each from 3 different countries, randomly select chairs at a round table that seats 9 people. Let the probability that each delegate sits next to at least one delegate from another country be m by n, where m and n are relatively prime positive integers. Find m plus n. To solve this problem, we need a principle called the principle of inclusion-exclusion. The principle of inclusion-exclusion states that for sets AI, for 1 is less than or equal to I is less than or equal to n, the number of elements in the union of the sets is equal to this formula. And in this formula, a lot of these types of terms are used. So this term just means that it's the number of elements in the intersection of these sets. For this problem, let's use complementary counting. Instead of calculating the probability that each delegate sits to at least one delegate from another country, let's calculate the opposite, which is at least one delegate does not sit next to some person from another country. And how many ways are there for that? For that, we can use the principle of inclusion-exclusion. All we have to do is calculate the total number of ways to seat them minus the number of ways that at least one person is not seated correctly, plus the number of ways that at least 2 people are not seated correctly, and minus the number of ways that 3 people are not seated correctly. For the total, there's just 9 factorial ways of arranging all 3 people, and since we can consider them to be indistinguishable, 3 factorial ways for each country to order them. To find the number of ways that one person is not seated correctly is, since if someone is not seated correctly, they have to be in the middle of a group, it has to be 9 ways to seat a group times 6 factorial divided by 3 factorial and divided by 3 factorial again. And this times 3 since we can choose 3 groups. For 2 people, there are 3 ways to choose the group that is still correct, and 9 ways to seat the first group, and 4 ways to seat the next group, and that's it. And for the last one, 3 people, there's only 9 times 2 ways. Since there's 9 ways to put the first group, then you can either put the second group here or here. Now, if we apply the formula, we get that the total number of ways is 1230. And the total possible combinations are 1680. Simplifying this, we get that our final answer is 41/56. And if we add m and n, our answer is 97. Let's end with a problem that uses recursions. A bug starts at a vertex of an equilateral triangle. On each move, it randomly selects one of the 2 vertices where it is not currently located, and crawls along the side of the triangle to that vertex. Given that the probability that the bug moves to its starting vertex on its 10th move is m by n, where m and n are relatively prime positive integers, find m plus n. First, let's find out what a recursion is and how to use it. A recursion is, as the dictionary definition, a method of defining something in terms of previously defined values. For example, for the recursion f of n equals f of n minus 1 plus f of n minus 2, with f of 0 equal to 0 and f of 1 equal to 1. Remember, we always have to define the first few values. And this one evaluates to 0, 1, 1, 2, 3, 5, 8. And these are called the Fibonacci numbers. Another recursion is g of n equals 4 times g of n minus 1, where g of 0 equals 1. And this evaluates to 1, 4, 16, 64. And this is a geometric sequence. And a of n equals a of n minus 1 plus 5, where a of 0 equals 0. This evaluates to 0, 5, 10, 15, 20, 25. And this is an arithmetic sequence. Coming back to the problem, we see that we can solve it pretty quickly with the recursion. Let's define a of n as the number of ways to go to A in n moves from A. And for B of n, let's define it as the number of ways to go to A in n moves from B. And similarly for C of n, but from C. Now, we know that B of n is equal to C of n by symmetry. Also, A of n equals B of n minus 1 plus C of n minus 1. Because the bug has to go from A to B or C and come back in n minus 1 moves. This value also equals 2b of n minus 1. Also, b of n equals a of n minus 1 plus c of n minus 1 by similar reasoning for a of n. And this equals b of n minus 1 plus a of n minus 1, which equals b of n minus 1 plus 2b of n minus 2. Now, we know that b of 0 is equal to 0 and b of 1 is equal to 1, since there's no ways to get from b to a in 0 moves, and there's one way to get from b to a in 1 move. Now, let's make a table of values for b of n, and once we get to b of 9, we can stop since a of 10 is equal to 2 times b of 9. After calculating a lot of values, we get that b of 9 equals 171. So a of 10 equals 2 times 171. And the probability is 2 times 171 over 2 to the 10th power. Since for each step, there's 2 ways to go. And we can cancel this with this to get 512. So our final answer is m plus n, which is 683. Thank you for listening. Please like and subscribe, and remember to click the bell icon for more updates.